In this video, I want to talk through a couple of problems that have to do with probabilities relating to the normal distribution. And I also want to address the issue of when to use the central limit theorem and when not to. So, an engineer is going to redesign an ejection seat for an airplane. The seat was designed for pilots weighing between 120 and 161 pounds. The new population of pilots has normally distributed weights with a mean of 126 and a standard deviation of 30.7 pounds. Okay, so before we look at the two questions, part A and part B, which I'm going to do below, if we just look at those first couple of lines, being told that the weights are normally distributed is important. So now we know we're using this continuous normal distribution graph as our model for probability. And we're not working with the standard normal distribution because the mean is not 1 in this, or the mean is not 0 and the standard deviation is not 1. In this case, the mean is 126 and the standard deviation is 30.7. So we have two problems here. In part A, if a pilot is randomly selected, find the probability that his weight is between 120 and 161 pounds. And in part B, if 33 different pilots are randomly selected, find the probability that their mean weight is between 120 and 161 pounds. So you'll notice the key difference between part A and part B. In part A, we're talking about a single pilot, one observation. If one pilot is randomly selected, find the probability his weight is between 120 and 161. In part B, we're looking at a sample of 33 different pilots. And we're looking for the probability that their mean weight is between 120 and 161. Okay? In part B, this is where we use the central limit theorem. It's the probability relating to a sample of observations having a mean weight, in this case between 120 and 161. I'm going to separate the screen into two halves. So I'm going to take care of part A on the left and part B on the right. Excuse me. Okay, so for part A, if a pilot is randomly selected. Now, we're using the normal distribution graph as our model. Now, the problem is find the probability. Now, remember, the words find the probability mean find the area under a portion of this probability density curve. When our sample space is continuous, probability refers to area. Okay, so the center of the graph is the mean, which is given as 126, the standard deviation of 30.7. And we're looking for the probability, or the area, between 120, which would be a little bit to the left of 126. So let's say 120 is about there. And 161, which would be way over here to the right. There's 161. So this red shaded area, is equal to the probability that X is between 120 and 161. And I just have these yellow cells over here on the left just to sort of organize the information that's given in the problem. It's not necessary, but I like to organize the information. So let me just record these four values. The mean is given, that's 126. The standard deviation is given, that's 30.7. And our two X values, X1 and X2, will be the 120 and the 161. Now we don't have to convert these X values to Z-scores. We don't need to standardize this distribution because we're using Excel. And Excel has a function for area under the non-standard normal distribution. So we're going to be using equal norm dot dist for normal distribution. We have to tell Excel the X value the mean and the standard deviation of the population. And then that last entry is whether or not we're using the cumulative function. Remember, 1 means yes, 0 means no. For continuous sample spaces, we always use yes. We always say 1 or yes, we're using the cumulative function. So that's not a question we ever have to address. It's always comma 1 as that fourth entry. And this will give us area to the left of this x value, whatever x value we put in here. Now the problem is Excel can't do this area between two x values in one step. We have to sort of do it in 2 steps. So we could start with this. Too much area. Everything to the left of 161. And then we can subtract off the area to the left of 120. And that will give us the area between 120 and 161. And so what we're actually going to type in is equal norm dot dist area to the left of 161 mean standard deviation comma 1, and then we're going to have to subtract from that the area to the left of 120. So that would be norm dot dist 120, same mean, same standard deviation, and then comma 1. All right, so this will give us the area between 120 and 161, which is the probability that the weight of one randomly selected pilot will be between 120 and 161. So let me just type that in. Norm.dist. So our larger x value is 161. Mean standard deviation, comma 1. And then from this, I will subtract area to the left of 120. So norm.dist 120, comma the mean, which is 126, standard deviation, which is 30.7, comma 1. So what I've just typed out is what I have written above in blue. And so there's our probability, about 45%. So we could, normally we round this to 3 significant digits. So we could leave it as is, but we could. We'll say about 0.450. Okay, so now moving on to part B. If 33 different pilots are randomly selected. So now this is telling us we're using the central limit theorem. Now remember, the central limit theorem is that the distribution of sample means, as long as the sample size is above 30 or so, the distribution of sample means will follow a normal distribution regardless of the distribution of the original population. Right? The distribution of sample means will be normal, even if the original data is not. Now, if the original data is normally distributed, we could drop the criteria that the sample size has to be above 30. So in this case, it is, but the sample size is 33, but we also know the population is normally distributed. Now, the central limit theorem says that the mean of the sample means will be equal to the population mean. But the standard deviation of the sample means will not be equal to the standard deviation of the population. It will actually be less. It will be equal to the standard deviation of the population, sigma, divided by the square root of the sample size. And so if we insert these two, if we substitute these two equations into our formula for the z-score, we get the z-score for each sample mean. This is to convert an x bar to a z-score, a sample mean to a z-score. So our z-score formula becomes x bar minus mu divided by sigma over the square root of n. All right, so we're going to need that here and here to convert the two sample means to z-scores. All right, so part B, just to pull the pertinent information from the problem, we get the same mean of 126, same standard deviation of 30.7. Now we have a sample of 33, so n is the sample size, 33. And we're looking for the probability that our sample mean is between 120 and 161. Okay, so our first sample mean would be the 120. The second one would be the 161. And because this normal distribution function that we just used in part A, that cannot be applied to sample means. That can only be applied to individual x values, individual observations. What we have to do is standardize these two sample means, convert them to z-scores. Okay, so let's do that. So the first z-score, so the sample mean of 120 converted to a z-score, that should be equal to, I'm going to use parentheses. So I'm basically, just so order of operations happens the way it's supposed to, I'm going to throw parentheses around the top and the bottom, the numerator and the denominator, as I type this into Excel. So equal, parentheses, x bar, 120, minus the population mean, so minus 161. We're going to divide that by sigma, which is the 30.7, over the square root. So the Excel function for square root is sqrt, square root of 33, square root of n. All right, so this will convert the first x bar, the first sample mean of 120, to a z-score. And that's a really large z-score in the negative direction. And then we'll convert the 161 to a z-score. Same calculation, except we'll do a 161 instead of a 120. So 161 minus the mean of 126 divided by the standard deviation, 30.7, over the square root of 33. And we should get a pretty large positive z-score here, and we do 6.54. Oops, my mistake. In that first z-score, I used the 161. If you look up here in the function bar, that 161, that actually should have been a 126. So let's go back and make that adjustment. 120 minus 120. Yeah, that z-score seemed a little too far in the negative direction. All right, that sounds better. Okay, so now we have these two z-scores, and normally we have z-scores rounded to just a couple decimal places, so we could do that with a couple of clicks. All right, so now we've got, instead of saying between 120 and 161, now we've converted those two sample means to z-scores. The center of the graph, since this is the standard normal distribution, is now 0. We have a z-score of negative 1.12 on the left, positive 6.55 on the right, and this area is going to give us the probability we're looking for. So since we've standardized our distributions, now we have the standard normal distribution. In this case, we have to use the Excel function for the standard normal distribution. So instead of norm.dist, we need a .s in there. That's how we tell Excel it's the standard normal distribution. So norm.s.dist for standard normal distribution. We don't need to tell Excel the mean or the standard deviation because it's always going to be 0 and 1. We just have to tell Excel the z-score and a comma 1. That'll give us area to the left. So we have to do the same thing we did in part A by using this function twice to find the area between two z-scores. So norm.s.dist first z-score 6.55. Now I'm rounding that. I could have used the exact value of the z-score by clicking on the location of the 6.55, but it's going to be about the same answer. So z-score, comma 1. All right, so that's everything to the left, all the area to the left of 6.55, all the way down to negative infinity. So again, we have to subtract off the area to the left of the smaller z-score. So that's going to be norm.s.dist. The z-score is now negative 1.12, comma 1. That will give us the area between these two z-scores, which is the probability that the entire sample of 33 pilots has an average weight or a mean weight between negative 120, which has a z-score of negative 1.12, and 161, which has a z-score of positive 6.55. All right, that does it for this problem. Just keep in mind, big picture, anytime you're dealing with a single probability involving a single observation from a normally distributed population, you're using the normal distribution as a model, this graph as a model. As soon as you start talking about a sample and a sample statistic, that's when the central limit theorem comes into play. And the central limit theorem is what I have here in black. Basically, this is, distilled down to its most succinct sort of representation. This is the central limit theorem. All right, that does it for this problem. I hope it was helpful.